Factors affecting solubility. Consider a saturated solution of barium sulfate, where we have barium sulfate solid in equilibrium with barium ions and sulfate ions. Adding one of the above ions to this solution would shift the equilibrium to the left, and the solubility of the salt will decrease. So, adding any soluble salt containing either barium or sulfate ions will decrease the solubility of barium sulfate. Example 1 of this common ion effect. Calculate the solubility of calcium fluoride in grams per liter in pure water, in 0.15 molar potassium fluoride solution, and C in a 0.080 molar calcium nitrate solution. The solubility product for calcium fluoride, CaF2, is 3.9 times 10 to the minus 11. All right, so first we're calculating the solubility in grams per liter in pure water. So we start with our dissociation of calcium fluoride solid into its ions, Ca2 plus 2F minus. KSP was given as 3.9 times 10 to the minus 11, and that's the concentration of the calcium ion times the concentration of the fluoride ion squared, given the coefficient in our dissociation here. At equilibrium, we have some unknown amount of calcium ion, which we call X, and fluoride ion, which we call 2X, given that for every 1 mole or 1 formula unit of calcium fluoride, we have 1 calcium ion and 2 fluoride ions at equilibrium. So we have the concentration of the fluoride will be twice as much the concentration of the calcium, so 2X. If we substitute X and 2X into our KSP expression, we get that KSP is equal to 4X cubed. Solve for X and get 2.14 times 10 to the minus 4. This is moles per liter. Okay, moles per liter because we were given a KSP value. Now, to determine the mass, so we just take our moles per liter, we multiply by the molar mass, 78 grams per mole of calcium fluoride, and we get a solubility in grams per liter of 0.0167. Okay, so now things get interesting. What is the solubility? What happens to the solubility of this CaF2 if instead of in pure water, we put it in a solution of 0.15 molar Kf. So Kf is a strong electrolyte. It will completely dissociate into ions K plus and F minus. So it is a major source of fluoride ions. What happens if we greatly increase the concentration of the fluoride ions to this 0.15 molar? We would expect the equilibrium to shift to the left and decrease the solubility of the calcium fluoride. The solubility product for calcium fluoride is given as 3.9 times 10 to the minus 11. The fluoride ion concentration is 0.15 molar. This represents the total amount of fluoride ions present in the solution and will be substituted into the KSP equation. So we start with our same KSP equation from the previous part, but we're given now this large concentration of fluoride ions. Now we solve for X. We get 1.73 times 10 to the minus 9 moles per liter. And the question is, what does that X represent? It represents the calcium ion concentration, right? And the calcium ion concentration is in a 1-to-1 ratio with calcium fluoride. So if this is the moles of calcium ion per liter, you could say that there's 1 mole of calcium fluoride per mole of calcium ions at equilibrium, right? And that gives us the moles of calcium fluoride per liter. Once I know that, I can find the mass of calcium fluoride by multiplying by the molar mass, 78 grams per mole, and I get 1.35 times 10 to the minus 7 grams per liter. So the solubility of calcium fluoride in 1.15 molar potassium fluoride is 1.35 times 10 to the minus 7 grams per liter. Part C, now calculate the solubility of the calcium fluoride in grams per liter in a 0.080 molar calcium nitrate solution. So again, calcium nitrate is a strong electrolyte, completely dissociates into ions. So we have a very large source of calcium ions here. If we have a really high increase or large source of calcium ions, we would expect the equilibrium to shift to the left and decrease. We should have fewer grams dissolved. So what is the concentration of that calcium ion? It's 0.080 molar. The solubility product for calcium fluoride given is 3.9 times 10 to the minus 11. The calcium ion concentration is 0.080 molar. This represents the total amount of calcium ions present in the solution. We can substitute that into the KSP equation. For each mole of calcium fluoride, 2 moles of fluoride ions are formed. And the solubility of calcium fluoride is half the amount of the fluoride ions. Calculate the solubility of calcium fluoride in grams per liter in a 0.080 molar calcium nitrate solution. So it's important to note that this 0.080 molar solution provides a large concentration of calcium ions. You can see initially I'm already starting out with some calcium ion. Then I have some change, X for calcium and 2X for fluoride, as some of the calcium fluoride dissociates so that we have at equilibrium 0.080 plus X for calcium ion and 2X for fluoride ion. Now, keep in mind this value of X is going to be very, very small because we're putting the calcium fluoride in a solution containing a common cation in this case, calcium. That will shift the equilibrium very far to the left over here, decreasing the amount that will dissociate. So this amount compared to 0.080 will be so small that we will say that at equilibrium, this is approximately equal 0.080. Okay, so let's look how we put this in our KSP expression. Calcium ion concentration at equilibrium, 0.080. Fluoride ion concentration at equilibrium, 2X squared. Solve for X, you get 1.1 times 10 to the minus 5 moles per liter. Now, what does this X equal? You can see here it equals the change for the calcium ion. And we can see that there's a 1-to-1 mole ratio between the number of calcium fluoride units and calcium ions. So for every 1 calcium fluoride unit that dissociates, we get 1 calcium ion and 2 fluoride ions. So this X will be how much of the calcium fluoride dissociated. So it's the concentration of the calcium fluoride in moles per liter. So if we multiply that by its molar mass, 78 grams per mole, we get 8.61 times 10 to the minus 4 grams per liter. Keep in mind the solubility of calcium fluoride in solution is half the amount of the fluoride ions. So if I needed to find the fluoride ions, I'd have to take this value of X and double it because we have that 1-to-2 mole ratio. The common ion effect states that adding a soluble salt containing common ions to an insoluble salt solution will decrease the solubility of the sparingly soluble salt. Compare the solubilities from the previous example. In pure water, the solubility of the calcium fluoride was 0.016 grams per liter. In a 0.015 molar solution of potassium fluoride, it was 1.35 times 10 to the minus 7 grams per liter, and in a 0.080 molar calcium nitrate solution, it was 8.6 times 10 to the minus 4 grams per liter. These results support Le Chatelier's principle. increasing the concentration of one of the common ions on the product side, either fluoride in this case or calcium in this last case, shifts the equilibrium to the left, decreasing the solubility compared to that of pure water. Changes in pH. The solubility of almost any ionic compound is affected by changes in pH. Consider the dissociation equation for magnesium hydroxide, where magnesium hydroxide, solid, dissociates into magnesium ions and hydroxide ions. When the pH is lowered, the solution becomes acidic. The hydroxide ions present in the solution are then neutralized by the added acid. Doing that will remove some of this hydroxide or decrease the concentration of the hydroxide. To compensate for the loss of hydroxide, more solid dissolves into the solution, shifting the equilibrium to the right. As a result, the solubility increases. Consider the dissociation of the salt calcium fluoride. When the pH is lowered by adding acid, the fluoride ions will interact with the hydrogen ion to form hydrofluoric acid. F- is the conjugate base of a weak acid, HF. As the fluoride ion interacts with the added hydrogen ions from the acid, F- concentration will decrease. The equilibrium will then shift to the right, producing more fluoride ions and calcium ions, increasing the solubility of calcium fluoride. Example 2, changes in pH. Calculate the molar solubility of manganese hydroxide in A, pure water, B, a solution buffered at pH equal to 9.5, and C, a solution buffered at pH equal to 8.0. The solubility product, KSP, for manganese hydroxide at 25 degrees Celsius is 1.6 times 10 to the minus 13. In pure water, as we're asked to find in part A, the pH is 7, and the hydrogen and hydroxide ion concentrations are 1 times 10 to the minus 7. The KSP is equal to 1.6 times 10 to the minus 13, and it is the concentration of the manganese ion at equilibrium times the concentration of the hydroxide ion at equilibrium. Remember, the dissociation looks like this. So we have X as the concentration for the manganese ion at equilibrium and 2X as the concentration of the hydroxide ion at equilibrium, though we know this is in pure water, so this is 1 times 10 to the minus 7. If we solve for X, put X in for the manganese ion, 1 times 10 to the minus 7 in for the hydroxide ion concentration, squared because of that coefficient of 2. And we solve for X, we get 16 moles per liter. So the molar solubility of manganese hydroxide in pure water is 16 moles per liter. So now let's calculate the molar solubility of a manganese hydroxide solution in a solution that's buffered at a pH of 9.5. At 9.5 pH, we can calculate the hydroxide ion and hydrogen ion concentrations using K water. This hydroxide ion concentration, 3.1 times 10 to the minus 5, is important. That's the initial concentration of the hydroxide. And then, of course, some of our manganese hydroxide will dissociate into Mn2 plus and hydroxide. We do start out with some amount of hydroxide based on the solution that it's in. And we have some of this that will dissociate, and the change there will be plus X or plus 2X, with an equilibrium amount of manganese equal to X and hydroxide equal to the initial concentration plus 2X. Now, remember, this amount is so small compared to this initial concentration that we will ignore it in our equilibrium concentrations. And then we can solve using our KSP expression. So KSP was given as 1.6 times 10 to the minus 13 equals the manganese concentration in equilibrium, which is set to X, times the hydroxide ion concentration, which is 3.1 times 10 to the minus 5 squared. Solve for X, and we get a molar solubility of 1.56 times 10 to the minus 4 moles per liter. All right, now let's calculate the molar solubility of manganese hydroxide in a solution buffered at pH equal to 8. That pH allows us to find the hydroxide and hydronium or hydrogen ion concentrations. This hydroxide ion concentration is important. And that's the initial concentration of hydroxide, because that's what the solution that we start with. And so remember that once that happens, some dissociation will happen of the manganese hydroxide. We don't initially start out with any manganese, but we have some change for every formula unit of manganese hydroxide that dissociates. We get a change of plus X for the manganese and plus 2X for the hydroxide, so that at equilibrium we have X concentration for manganese and the initial concentration plus 2X for the hydroxide. Keeping in mind, of course, that this change relative to the initial amount is essentially zero. All of the hydrogen ion concentration comes from the pH of the solution. And so we can use our KSP expression, and the value of KSP that was given, 1.6 times 10 to the minus times 10 to the minus 13th, equals the manganese concentration at equilibrium, which we set equal to X, the hydroxide ion concentration, which is given as 1.1 times 10 to the minus 6. We need to square that from our KSP expression and solve for X. We get 0.16 moles per liter. If a substance has a basic anion, like the manganese hydroxide that we just were discussing, it will be more soluble in acidic solution. On the other hand, if a substance has an acidic cation, it will be more soluble in basic solutions. We will discuss in the next few slides the effect of pH changes on substances that are amphoteric, those substances that can act as both acids and bases. Some metal oxides and hydroxides are more soluble in strongly acidic and in strongly basic solutions because they can act either as acids or bases. These substances are said to be amphoteric. Examples of these substances are oxides and hydroxides of aluminum, zinc, and tin 2+. They dissolve in acidic solutions because their anion is protonated by the hydrogen ion and is pulled from solution, causing a shift in the equilibrium to the right. For example, aluminum hydroxide, solid, dissociating into aluminum ions and hydroxide ions. These hydroxide ions are neutralized by the hydrogen ions in an acidic solution that would decrease the amount of the hydroxide ion and then shift the equilibrium to the right, making aluminum hydroxide more soluble in acidic solution. Many metal hydroxides dissolve more strongly in acidic solutions. Calcium hydroxide, iron 2 hydroxide, iron 3 hydroxide are only more soluble in acidic solution, not due to their amphoteric nature, but due to the hydrogen ion interaction, similar to the above reaction with aluminum hydroxide that we discussed on the previous slide. However, these oxides and hydroxides also dissolve in strongly basic solution, and this is because they form complex ions. So the metal ion in the compound can be bound to 4 or more hydroxide ions to form a complex ion. Aluminum ion reacts with additional hydroxide to form a complex ion when a base is added to the solution, as in the following reaction. So Let's assume I have an equilibrium solution of aluminum hydroxide. And then I add more hydroxide, making the solution more basic. And these aluminum ions can form a complex ion with that excess hydroxide, forming this AlOH4 with an overall minus charge. As a result of the formation of the complex ion, AlOH4 minus, the solubility of aluminum hydroxide increases. When more hydroxide is added to the solution, making it more basic, aluminum ions form the complex ion, shifting the equilibrium to the right. When the equilibrium shifts to the right, solubility of the salt increases.